Okay, what's going on, my friends? How's it going? I am back from the US and a fucking amazing time. I had never actually been to the States before this trip. So most of the time people will go to the States to do the generic touristy places, New York City, Vegas, some Chicago and other bits and pieces like that, Miami. I went and dove into the deep end and pretty much went to real life working, just like not a touristy area. Went to Oklahoma City. And then to Dallas, which was a bit more touristy. We went to a big hotel in Dallas, but no, the time in Oklahoma was absolutely fantastic, and I will definitely be back, I think, in possibly May 2019 for some stuff with DD, which will be really cool. So let's see what we've got going on in the live chat this evening. But we're going to be looking at a not a repair this time. This is actually so Speaker Freak is in the chat now. This is actually, we're looking at an amplifier that belongs to Speaker Freak in the chat. Need to change my. That's not the one I want. I wanted the handheld. There we go. So this is a JBL GTO 14001, and I need to change the current amp because that's not correct anymore. It is a JBL 14001. And this is actually going to be not an amplifier repair, but an amplifier potential upgrade. So, my foot pedals are not working properly. That's better. So yeah, this amplifier actually works fine. Nothing wrong with it at all. However, Speaker Freak wants to see whether we can make some upgrades to make this amplifier run reliably at 1 ohm. Now, if you know the JBL GTO 14001, then you'll know that it is a 2 ohm stable amplifier only. However, it is a very, very good 2 ohm stable amplifier, and it has the ability to run a static load bench test very happily at 1.3 ohms. Which is very low indeed, and it does about, I think it benches something crazy like 2,200 watts RMS at 1.3 ohm static load on a bench test, which is pretty nuts. So to run reliably at 1 ohm, however, when you try and bench test it in its standard form at 1 ohm, it is not particularly happy about that. So what we're going to do is we're going to try and perform some upgrades to make it more happy at the lower impedance, a reactive load of 1 ohm. Now, when you run the amplifier at 1 ohm in a vehicle, the chances of the amplifier actually seeing 1 ohm are very small, because after impedance rise, you're more than likely to see above 1.3 ohms anyway with a reactive speaker load. However, I would like to just make it so that it is able to drive a 1 ohm load, because that is, at the end of the day, that's what's called a 1 ohm stable amplifier. Is the idea is that it can drive a 1 ohm static load reliably for a long period of time without any issues. So that's what we're going to try and do. So because this is a very good starting point, the JBL amplifier is very good already. I don't think we're going to have to do many crazy upgrades here. I'm thinking all we're going to probably need to do is replace the output FETs with something higher current handling. We're probably going to thicken up the traces on the back of the board and things like that. The transformers and inductors actually look pretty decent for about 2.5k already. JBL used some pretty nice transformers and inductors in here already, so we shouldn't really need to change much in the sense of the inductors or the transformers. They shouldn't saturate with current. We should be good to go with that. So yes, output MOSFETs we need to change. We might have to modify the drive circuit if the drive circuit isn't happy. However, the drive circuit of these JBL amplifiers are actually very strong. You don't know how well you'll be able to see this in here with my head cam, but there's a little chip that sits on the driver board, and this is an IR2010S chip, and there's two of these. One, because this is actually, I think this is a full bridge amplifier. Yeah, I think this is a full bridge amplifier. So basically, yeah, you have one chip per sort of bridge half, if you like. And these 2010S chips are very powerful and able to run some pretty high input capacitance FETs, which means that we can run some pretty bad boy FETs in this amplifier, and the driver circuit should be pretty happy. Once we've upgraded the output section stuff, we'll have to go ahead and upgrade the power supply MOSFETs as well. So we've got 8 what are usually 3205s in here that we'll want to change so that they are a higher current. And what we'll also want to do is on the back of the board, we want to jump over these fuses. So we want to completely remove the onboard fuse section of this amplifier so that power goes straight to the board, and then the idea is that the user runs an inline fuse like the most other amplifiers. Like I've got a Sundown 6K sitting down there. Most big amplifiers don't have fuses on the board in themselves. They, you use an inline fuse. So that's what we're going to do here. We're going to take the onboard fuses out of the equation, jump over the trace so that it's a nice low resistance connection, because having these 440 amp fuses probably isn't going to be enough for 1 ohm operation. So what we got going on over here, yo. If you kill it in the process, don't worry, keep it for spares, says Speaker Free. Oh no, don't worry about that. The chances of us killing it in the process are very, very small, but if it does get killed in the process, then it will literally just be FETs that get taken out, because we have the high protection circuit power supplies and stuff like that. So if for whatever reason, as we're upgrading it, some outputs do die, or power supply FETs die, or anything like that, it'll be a very, very simple non-dramatic issue where you just replace the FETs and it's good. So yeah, we won't keep this, we won't write this amplifier off. It's perfectly working now. We're going to make some reliable upgrades to it. We're going to monitor our upgrades as we go along and monitor the voltage drop across different parts of the board and see how we get going. What I think would be really interesting to do is to bench test it at 1 ohm and 1.33 ohms first before we make the upgrades, so you guys can see how much more power we get from the amplifier after making the upgrades. However, that's what I forgot to say, is that this isn't what we're going to be doing in this video. This video is just like, hi guys, I'm back from the US because I'm kind of sleepy. So this video is just going to be like a little pre-introduction intro thing to me live streaming again after getting back from the US and sorting out some shit I had to sort out. And so this upgrade will probably be my next major live stream, which I might actually do later on this week. But what I wanted to do in this live stream was just to answer any of your guys' questions about my trip to the US, if you had any, and talk about that if you like, and also to make some preparations for this amplifier upgrade. So what we're going to do is we're going to have a look at what MOSFETs it's actually using at the moment, and then we're going to come up with some good replacements. So if we take a look at the output FETs by removing this one, and take a look at the power supply FETs by removing this one. Our DD-M5 safe at 96 volts output. That doesn't really make any sense. You can't say, is my amplifier safe at a certain voltage worth of output. As such, you need to know whether it's clipping or not. And the clipping point will vary depending on your input voltage to the amplifier. So the amplifier will clip at a higher voltage with 14.4 volts going into it than it will do if you drop to 12 volts. So without the subs connected, if you run your amplifier up to clip point, you might get, I don't know, if not talking about the M5, just any amplifier. Let's say an amplifier gives 100 volts AC at clip point at 14.4 volts with the speaker disconnected. As soon as you plug the speakers in, there's voltage drops across the rails and all sorts of other stuff going on, and the amplifier may then clip at like 85 volts AC. So you need to check your clipping with the subs connected, and you can't really say, oh, you can't disconnect your subs and measure the voltage out and say, oh, this is how much power is going to my subs, because your load is reactive, so you can't calculate it without an ammeter and knowing the current, and without the speakers connected, there is no voltage drops across the rails, and it's a completely different story. So you just have to, generally turn the amp up until the amp starts sounding bad, because you can hear the clip from the board of these Class Ds, or until the speaker starts sounding bad, or until it starts smelling, and then turn it down. Easy peasy. Once you get good with audio, once you've installed a few setups, or you've had a few setups and you've messed around with your amp settings a fair bit, you kind of get a feel for it. You get a feel for like, am I pushing amp into clip? You can hear it, you know what it sounds like, or this is a bit too much power for my subs, because you really catch on to the smell of it, or they don't sound that great, or maybe they're moving too much, and so you get a much better feel for it. Don't buy a DD1. No. Do not buy a DD1. If you want to actually detect clipping, then watch my video on YouTube called How to Detect Clipping Without a DD1. And my method will cost you a couple of bucks and is super duper simple, and a little easier to, you can hear the difference in distortion with my method, whereas the DD1 is just an LED that's either on or off, whereas with mine you can actually literally set your amp to a rough percentage of THD. So, okay, let's have a look. What FETs do we have in this amplifier that we're going to be upgrading? Let's take a look. So the outputs on this, now this is actually using some pretty decent output FETs already. Zoom in with my head here. Okay, I'm going to actually take my hat off and just use the camera to zoom in here. So the output FETs of this amplifier, ooh, they're different batches. They're very different batches. That's really interesting. I don't think this amplifier's ever been repaired. I think this amplifier is factory. So, I mean, this is probably fine. JBL are pretty good old boys. So if these are different batches, then I'm sure they probably tested the VT and other bits and pieces like the RDS to confirm that these were actually well matched before they dropped them into the amplifier. But yeah, we've got mismatched FETs from factory. Not always a problem. If the VT and the RDS is close enough to each other, then they will work in parallel, but it's just kind of like, I don't like it, you know, it's just kind of, I don't know. It's not nice to see, it just makes me feel uncomfortable. Buenos tardes, buenos noches, aquí es a las 12:15 o 1 menos 10 por la mañana o en la noche aquí, y necesito cama en unos minutos. Anyway, so yeah, these are, we've got, what by the looks of it, we've got so these four are all matched. These four are all matched here. So this is one half of the full bridge, and you got this other half here, and it looks like we've got one from this side and then three of another batch. I'm sure they're probably fine. We can actually test to see whether they're fine. Do you want to see whether these are fine? So this amplifier came in. I don't think this has been prepared before. All right. So let's just see whether having these different batches in the amplifier actually was ideal or not for this one. So what I'm gonna do here is I'm gonna pull the MOSFETs away from the heatsink slightly, okay, so that they have no heat sinking at all. Because the reason I'm doing that is because we're looking for uneven heating of these. So because these FETs are from different batches, if they have slightly different characteristics, slightly different turn on voltage, gate turn on voltage, being used in the same parallel bank, the one that is out of sync with the rest of them will start getting hot because it's being powered backwards from the rest of them being turned on at a time when it shouldn't be, etc. So let's pull the FETs away from the heatsink like this just now. So all away from the heatsink, and I'm going to plug the power into this amp, turn her on, and I'm going to use my thermal imaging camera to see whether it'll probably be one of the FETs in this four here, because in this parallel bank of four, we've got a mismatched FET. So I wonder whether that was actually out of balance or not from factory. Interesting if it was. Very interesting if it was. I have my inklings. I don't think it was. I think it's probably fine. Yes, they're a different batch, but I'm sure they're probably matched enough to work fine. But the curiosity's got the better of me now, so let's plug the power in. Let's turn her on. Turn this to my other view, top port scope. Here we go. So we can see that we've got 10 volts and 0 amps going in at the moment. Bought it second hand, might have had a repair before, but couldn't say for sure. It doesn't look like it's been repaired. Generally, once you get to see a bunch of these amplifiers, you can tell the difference between factory soldered connections and repaired soldered connections. There's kind of telltale signs as to whether the thing's been unscrewed before. So another reason I don't think this has ever been repaired is because the glues on all the screws here are still perfectly intact with no breaks in the screws to the glue, like the Loctite, whatever it is on top that's on the screw. So this has never been taken apart before. So yeah, this definitely, almost 99% sure this has not been repaired before. So yeah. Let's turn her on and see if we have any heating on those mismatched FETs, just out of pure interest here. Get the old thermal imager. Amps turned on. As you can see, we have 1.5 amps worth of current draw on idle. Let's take our oscilloscope probe and just confirm that we have output section switching. Oops, that's the wrong probe. That's the green one, not the purple one. So we have rail voltage, and yep, we have output switch. So yeah, the thing's working great. So let's have a look then. So we've got 10.2 volts going in. So I'm going to actually crank this up, and I'm going to give it like almost 15 volts here. There we go, 15 volts. And that should show up any differences with these FETs here with the thermal imaging camera. So you can see on the screen here, the thermal imager, you've got some blotches that are getting hot. So those blotches that are getting hot, that's part of the driver board. The drivers, the IR2010S chips, they run kind of warm. You should see about 40 degrees on these when it's running with like a high 14 or 15 volt input to the amplifier. But the FETs themselves are staying nice and cool. So it looks like that having these different batches in this scenario was not a problem. They are close enough matched that they run perfectly together without any heating due to mismatched specifications. So I think one of them's getting slightly warmer than the other. Only very, very marginally. Very, very marginally. Not enough to be causing any problems whatsoever. So that's cool. Good to know. So not always when you see mismatched batches is it going to be a sudden instant problem, but I still don't like it. It makes me feel uncomfortable. So anyway, yes, these are IXTP 50N20Ps. Now, if you have been working with the MOSFETs for a while, then the ones that are named like this, with a number and then a letter and then a number like 50N20, that most of the time that means this is a 50 amp FET, N channel MOSFET, and 200 volts. 50N20, 50 amps, N channel, and then the 20 is 200 volts. So if we want to make upgrades to these on the output section, we need to find something that is higher than 50 amps, preferably, and that has a lower RDS rating than these ones, which means that it will run cooler. Also, other specifications that are useful to us in terms of them working well in the circuit is having a similar total gate charge value and input capacitance value. Another thing which is worth looking at is not just how much current the FET can pass, but at what voltage does it pass that current. So you might have a 200 volt FET, you might have two different FETs, both of them 200 volts, right? One of them has a higher current rating than the other. However, the one with the lower current rating does more current at the voltage you're going to be using it at than the one that does higher current, and that one will do the higher current at a lower voltage than you're going to be using it at, so it's not useful in your circuit. So there's a whole bunch of stuff you have to look at when you're looking at changing FETs. So we're going to go ahead and have a look at some FET specification sheets and see what ones will best fit in this. And also on the power supply, we have to do the same thing on the power supply, which are these ones. I'll take the hat off again and have a look. So when this focuses, the power supply MOSFETs here they're the good old classic IRF 3205s. 3205s are nice and reliable, and they're used across the board these days, but there are better ones out there that can be used. The 3205s, from memory, they are a 110 amp MOSFET, and I think they're 60 or 80 volts. I can't remember, one of the two. They're like around 60 or 80 volt FET, and I think 110 amp. So yeah, there are some upgrades we can make here. So let's go ahead and have a look on the interwebs and find a suitable replacement. Let's just quickly check the chat. Sorry to be a little off topic, but have you ever worked with a Rockville amp? I have one in my car, bought new, knew very little about it. Look about this thing. They look a little too good to meet rating. Yeah, so no, Rockville I think are just like obvious rip-off of Rockford, I think, and from what I've seen, I've never worked on one on the bench here. We don't get them in the UK so much, if at all. Actually, I don't think there are any or much at all in the UK. But from what I've seen of photographs of the boards and stuff, they're just really shitty, generic Chinese, crappy boards. So yeah, they're nothing special at all. But if you get them for cheap enough, and they do a fair bit of power, then okay, whatever, you know. There's a point when a shit amp becomes like, maybe that's okay to buy if it's like really, really cheap enough, because at the end of the day, power is power. And yeah, it might not last very long, but you know, if you just need power for the least amount of money, then sometimes these cheap, shitty Chinese brands can be good value. Do you sell amplifiers or is it just repair them? No, I sell them as well. I tend to buy blown amplifiers occasionally from the internet, eBay and stuff like that, and I'll repair them. Usually the amplifiers that I buy myself, I end up doing a Boozy live repair video of that. So if you type into YouTube barevids Boozy, B-O-O-Z-Y, then you'll see some of the amplifiers that I have purchased myself for repair that I repair and sell on. But because they belong to me, I have a few drinks and we have a great evening on live chat and on the stream, and I'll try and repair it after many glasses or bottles of wine, which is always good fun and games. And then yeah, if the repair is successful, then yeah, we bench test it, endurance test it and sell it on. After seeing some amp dynos, they seem to do just underrated. 4K RMS, even if it ends up only being 3, costs 220, which seems a good way to go. Yeah, that's the thing, Jonathan. They'll do good power for the money, but the amp might not last very long. And especially if you mount the amplifier to the subwoofer box, these Chinese cheap amplifiers have absolutely very shitty build quality in terms of vibration damage prevention. So keep it off the box and keep it, you know, out clipping and stuff like that, and you should be fine. Are Amplifier amps any good? Amplifier are actually a brand that I did look into contacting to get a couple of samples to see whether they wanted to distribute the stuff in the UK, but they never responded. So I've never seen the Amplifier stuff in person, but from what I could see on their pictures, it looked like good old Korean stuff. I think I think it was like a year ago now I looked into that. So, but from memory, the Amplifier stuff is actually pretty decent. Can we log how hot the amp gets before and after the upgrade? Yeah, we can do that. So when I actually go to do this this amplifier upgrade, we'll do a sort of endurance test on it with a static 2 ohm load, and we'll see how hot it gets after a set amount of time. And yeah, then we'll do the same after the upgrade and see how hot it gets after the upgrade. Okay, so yeah, we've checked that these different batches of FET weren't a problem, which they weren't. What was the next thing I was going to do? Oh yeah, right, that's right. So we're going to have a look online, and we're going to see whether we can find some replacement MOSFETs for this that will be good. So let's take a go over to Firefox here. We're going to go ahead and hit up RS Components, which is the website that I use. This website a lot in the UK. It's very good, very cheap prices, free next day delivery as well, so very useful. This is going to be annoying because it's going to, every time I type on my keyboard it changes my camera. So let's bring up first of all a spec sheet for the FETs that are currently in this amplifier. So we've got an IXTP 50N20P. So let's have a look at this first and get a reference point for these. IXTP 50N20P. Okay, wicked. So yeah, these are 50 amp 200 volt FETs. TO220 package is the one that we're looking at. So let's have a look. RDS which is important, on. So this is the resistance of the MOSFET when it is told to switch on. So the lower this number, the better, because obviously resistance creates heat. So the less resistance you can have when the FET's turned on, the cooler the FET will run. That is provided your drive circuit can drive it. Low resistance FETs, low on resistance FETs generally tend to have very, very hard to drive characteristics. So you have to also watch out for that. So these aren't as important here. The voltage gate source, so this is the voltage that the gate needs in order to turn the FET on reliably, is between 2.5 and 5 volts, which will generally be roughly the same. The drive circuit will be fine for that. So let's take a look at our gate charge. So our total gate charge, which is which one is it? I can't remember. Now the CISS is the input capacitance. So this is one important. This is kind of showing how much of a pain in the arse the FET will be to drive by the drive circuit. So with a FET, if the gate on a MOSFET is capacitive, it almost acts like a very tiny capacitor. So when it receives a charge, it will actually maintain and it will hold some of that charge. And so when the drive circuit turns the drive wave off, that charge will remain and it will go back towards the driver, or it will need to be pulled down through a pull-down resistor or through like a diode that's in line with the gate resistor. So the higher the capacitance of the gate, then the more bullshit and ringing and stuff that you've got to try and sort out and tame when the FET is being driven. And it makes it a pain in the arse to drive these FETs very quickly, because obviously the faster the drive wave, the faster the switching speed of this MOSFET, the quicker you need to get rid of that gate capacitance, that remaining residual current on the gate, and also the quicker that you need to be able to charge the gate, because obviously if the gate is if it doesn't have any charge on it at all, if it's kind of a high capacitance, then when you try and drive it with the drive signal, it will take longer to ramp up because it's capacitive. So there'll be a kind of ramp up time between when the drive signal says turn on now and the FET actually turns on, because the gate capacitance is quite high. So the lower this is, the better really, the easier it is to drive. And also the I think it's the, here we go, the NC. So yeah, the QG on the QGS, this is the total gate charge. So we've got 70 NC, and this is how much charge the gate needs before it turns on. So again, the lower this number, the better, because it means that it's easier to drive. It doesn't need quite as much energy from the drive circuit to turn on. It will require less current from the drive circuit to turn on. So these are pretty respectable numbers. This gate capacitance is quite low indeed, and the gate charge is average. It's not bad. I've seen like gate charges way down in the 30s, so this is okay. This is average sort of gate charge. But we do have this circuit being driven by IR2010S chips, which, as I said earlier, are very powerful, and so we should be able to run some pretty high value input capacitance and gate charge FETs on this drive circuit without running into too many hiccups. So okay, now that we know what the originals are running at, let's go over to RS components and let's take a look at some replacements and see what we get. So we're going to go ahead and take discrete semiconductors. Let's just quickly check the live chat. Have you ever thought of building your own amp? Yes, Jay Holly, I have definitely thought of building my own amp, but it's not something that I'm quite there with yet. It's like, it's one thing to repair an amp, but to design an amplifier from the ground up, from scratch, is a completely different skill set and requires a lot more experience and knowledge. So I'll get there eventually. I probably will design my own amp eventually, but not for a few years, I don't think. I'm after a 3K amp at 2 ohm or 0.5. What would you have or recommend? Well, if you're in the UK, then I can sell you something probably, but if you're not in the UK, then I can't. But yeah, if you want 3K, right, it depends what you're running. And this is another video that I want to do on. People always ask, oh, will this amp run 0.5? Is my amp good at 0.5? Can I get away with running my amp at 0.5? Generally, so yeah, there will be amps that are maybe better suited to running a lower or a harder load, a lower impedance than others, but the majority of the time it's not your amp that allows you to run 0.5, it's your sub setup that allows you to run 0.5. Okay, generally amplifiers, no matter how good they are, sundown, DC, digital designs, whatever, great amplifiers, they will not be reliable running a static, legitimate 0.5 ohm load consistently all day long, daily. You can do on a bench test maybe for a little burst, but if you try to run on a legitimate 0.5 load all day long at all frequencies, the amp will overheat and the FETs will die. That goes for pretty much all amplifiers that are 1 ohm rated. Trying to run it at half ohm if it's a 1 ohm rated amplifier. The thing that allows you to run amps at 0.5 is your sub setup having a great enough impedance rise that causes the amplifier to never see the 0.5 ohm resistive load. So generally, people that are running good, expensive, high power amplifiers like Digital Design, Sundown, DC Audio, etc., Ground Zero, they will generally be running high power, high motor force, high inductance woofers that do present a higher impedance to the amplifier. Whereas you get the cheaper, the guys who are on more of a budget, they buy cheaper, lower motor force, lower inductance woofers, and maybe smaller enclosures because they're trying to keep it in the boot, and then they buy an amplifier that's maybe cheaper and not quite as sturdy. If that setup is then run at 0.5, you have an amp that's less capable with a hard load anyway to start with. You have low inductance woofers that are not going to give a high impedance rise to the amplifiers. The amplifier's under harder strain than the big amplifiers would be. And you have a small enclosure, which means that the woofer doesn't move as much because impedance rise is tied directly to cone movement. So the more the cone and the coil moves, the more impedance rise you'll have, which is why you get the lowest impedance rise at box tuning when your cone is held still by the port load, and you get the most impedance rise either side of tuning, either when you unload or when you're playing above tuning and the woofer starts to move more, up to a point where the frequency is so high that the cone doesn't move much. There's like the kind of graph for impedance rise starts off high, gets lower, the lowest is your box tuning, and it goes up again, then it starts to taper off as the frequency gets higher and the sub starts to move less with a higher frequency. And then your coil is just then turning into an inductor and filtering the frequency in the first place, turning into heat. So if you want a 3K amplifier, it depends what your subs you're running. If you're running good high motor force subs, then you could get away with a fairly decent 3K amp running at 0.5, 1 ohm amplifier. However, if you need a 2 ohm load, I would possibly suggest the Banda Ice 3000, something like that, or the Banda Ice 3500, because they make that in a 2 ohm version, and the Banda board designs are the best board designs that I've ever seen come out of Brazil. Much better than the Taramps, because the Taramps have power supply design flaw on the transformer. It's not right for it. The power supplies are fucking terribly unreliable in the Taramps. Stetson, they have build quality issues with the vibration damage and other bits and pieces. They're just not built the same as the Banda. The Banda stuff is fantastically built. It's just a shame that they've had quality control issues with where they get the MOSFETs from in the past. But yeah, I would look at maybe a 2 ohm Banda in your scenario. Anyway, so where were we? We're looking at these MOSFETs. So let's go back to our replacement MOSFETs for 1 ohm load on this JBL. So we're going to have a look at obviously MOSFET transformers here. And now RS Components is going to give us a horrific list of 11,000 products, which is obviously no use to us scrolling through. So we're going to filter by the voltage we need, the current we need, and the package that we need. So let's first of all go pin count, because we're going to have 3 pins. I'm going to just tick all of the ones that are 3 pin here, because sometimes they get put into the wrong category. So our MOSFET needs to have 3 pins. It also needs to be package type. It needs to be a TO220 or similar. So let's go scroll down to TO220, which is what these are. So TO220, TO220AB, TO220. Now TO220F, I think they have a closed back. So that's not what we want. I can't remember what SIS is, so I'm going to tick that anyway. So that's our package type done, filtered. Now, our MOSFET needs to be it needs to be 200 volt MOSFET. So the Maximum drain source voltage needs to be 200, and we're also going to include some 250 volts as well, just in case there's anything decent up on the 250 volt mark. And what other bits and pieces are we got in here that we should start looking at? So we've narrowed this down now to 114 products, which is still quite a lot. So if we look at our maximum continuous drain current, perhaps we can filter out all the super low current ones there that we don't need. So if we go from, so the current MOSFET is the amplifier 50 amp. So in order to make this better at 1 ohm, I would say we want to be looking at like 50 amps and above. 60 amps and above. So let's go for 60 and above. 60 to, and then the maximum on this list is 88. So apply filters. We've got 26 products left now. That's much more manageable. We can really start to have a look at some of these. And I'm going to organize it by maximum continuous drain current. First of all, I'm going to start off with the highest, which should be 88. All right, here we go. This is now starting to look promising. So we also need to start looking at the price, because these high current drain MOSFETs get kind of expensive. £4.31 each. That's before VAT and taxes. So that will probably end up at over £5 or £6 a FET. So we need 8 of these. So whatever price you see here, add about 20% and times it by 8, and that's how much the output section upgrade is going to cost in terms of MOSFETs. So the first one on this list is very, very high current. And what we're going to do is we're going to scroll along here and see some of the other specifications of this. So yes, we have 88 amps, good. N channel, which is correct. 200 volts, which is what we want. Maximum drain source resistance is 11 milliohms, which is teeny, teeny, tiny. When we compare that to the RDS of the FETs which are currently in amplifier, that is 60 milliohms. So that's almost 6 times lower resistance, which means it's going to run way cooler potentially than the original ones in this amplifier. So that's good. However, as I said earlier, with a low on resistance comes horrific stuff with it being driven. So I wonder, do they have those specs in here? No, they don't. Okay, so what we're going to do is I need to open the data sheet for this one. So if we open this in a new tab, and we want to open the data sheet for this, and take a peek at the gate charge and the input capacitance. 10.7 milliohms is actually even lower. So let's scroll down and take a look. It will still do 63 amps at 100 degrees Celsius on the FET when this amp is cooking up like a boss. Let's take a scroll down even further. So up. Drain source resistance state. Yeah, this is the RDS specifications. Let's go down further and take a look at input capacitance. Oh, that's not too bad, you know. That's actually not too bad. I was expecting that to be quite a bit higher, to be honest. Typical input capacitance is about 5.3 PF, and the maximum that we should see on any FET is around just over 7,000. Which is, I think, that is within the limits of this 2010S driver chip. I think that shouldn't have any problems. The rise time and fall time, that should hopefully be kind of similar. I mean, the switching frequency isn't that fast in these amplifiers, so they shouldn't really play into much factor at all. Oh, god damn, look at that. Total gate charge, 65 typical, 87 maximum. That's actually, the typical is lower. This is a damn good. This is a crazy FET. This is actually very, very nice. This is actually lower than our original one, which was a gate charge of 70 typical. So yeah, it looks pretty promising, this one. However, if you noticed, this also has a power rating associated with it. So if we scroll along right to the end again, you can see here that these have a maximum power dissipation 300 watts. So this top one will do 300 watts. This next one down, even though the next FET down, oh no, hang on, they're all 88 amp. Okay, I might be chatting shit here, wait one sec. So the next one down in terms of current handling is 84 amps. And that is also 300 watts. So that one will likely do its higher power at a different voltage than the 88 amp one, and that's important. That's what we need to check. We need to make sure that this is going to be doing its maximum drain current rating at the voltage that we're going to be using the MOSFET at. Now, if we take a look at the amplifier itself, we can actually power the amplifier up and see what kind of voltage these MOSFETs need to be able to do their power. So if we turn the amplifier back on, I'm going to give the amplifier its kind of normal voltage from the car, which is generally around 14 volts. So let's crank that down to about 14.2. Take our probe and let's zoom in on the scope, and let's see what voltage this FET needs to be able to do its power. So we have 73 volts RMS, which is the RMS voltage of this square wave. However, the rail voltages are plus and minus 62 volts. Okay, so these are 200 volt FETs, and the reason that they need to be 200 volts is because, yes, we've got 62 volts on the positive rail, and we've got negative 62 volts on the negative rail. So the difference between those, it's the difference between those two voltages that is important. So yeah, the difference between minus 62 and positive 62 is 124. So yeah, the FET needs to be able to be happy doing lots and lots of current at between 100 and 124 volts. So looking at this, we could possibly get away with running 150 volt FETs. So the lower the MOSFET, voltage rating, generally you tend to find higher current models. So if we were to drop down to a 150 volt FET, then we might actually find ones that do higher current. So maybe we could check that out. It's better generally for reliability going for a higher voltage, having more headroom in the FET's voltage range, because if there are any spikes or anything on the drive or any spikes on the rails, then the FETs don't explode quite as quickly. But yeah, I think in order to get higher current ratings, we probably could go down to 150 volt FET on here. But yeah, so looking at that, then we need the FET to do good power at between 100 and 125 volts. So let's take a look at this bad boy one we've opened first. In order to look at the voltages versus the current, we need to take a look at the graphs down here. So there's going to be a bunch of different graphs here. We're going to skip through them here. So we've got this is power output versus case temperature. So TC is temperature case, and P is P total, power total output, power dissipation. So you can see there that the power starts to drop off from 300 watts. As soon as it starts reaching above 25 degrees Celsius, it starts tapering off until you get to like at 100 degrees here on the case of the MOSFET. The thing will literally do the half its power that it was able to do at 25. So it's important to keep these FETs cold. So let's have a look. We've got ID. This is drain current versus temperature, so that's very much related in a similar looking graph to the total power output, as you'd expect. Safe operating area. So this is the voltage drain source. This is kind of the thing we're looking at. So this is the voltage drain source versus how much current it will do at that voltage. So the higher the voltage that we go, I think this is, hang on a minute, is this what the one we're looking for? These graphs are still ever so slightly confusing to me sometimes. So we've got 10 to the 0, 10 to the 1 would be what, 10 volts? The standard form is, I haven't done standard form in years, but I think 10 to the 1 is 10, and then 10 to the 2 is 100, and 10 to the 3 is 1,000. Yeah, that looks about right going by where this, because yeah, 100, and then 200 will be there, because this is a logarithmic graph. So we've got 100 volts, 100 volts, 200, 3, 4, 5, 6, 7, 8, 9, 10 till we get to 1,000 up here. So yeah, this is 100 volts and this is 200. So our range is going to be between 100 and 200 volts. So if we take a look at our graph, if we go up, and it also depends on the speed of our drive wave, which we can check as well, because obviously the longer the FET is left on, then the lower current this thing will be able to do at this voltage. So this bottom one on the graph here, you can see says DC. So if you were to not actually drive this FET at all, if you were just to turn it on fully DC, then you can see there how the current drain changes with the voltage. Now our drive wave, if we go back to the other view here, our scope cam, if we turn the drive wave on, I've got to kind of get this right. So we are looking at 1 US. So we've got our drive is, well actually we can go by the frequency. So we've got 175 kilohertz, which is that's 175,000 cycles per second. Okay. So that is, can somebody help me out here? That is, where will that be on the graph? That's 500 nanoseconds per, hang on, that's right. So each cycle, by the looks of this, is just a tad longer than 500 nanoseconds, okay? So let's take a look at that on the graph. Okay, so it's actually pretty fast, I think, by the looks of it. It's actually, no, because the FET is only left on for, half of that cycle, because the other half of the cycle is off. So I think that's going to be way up above. So I think we're looking at the top end of this graph. I think. Yeah, we're looking at the top end of this graph, I think. So yeah, at 100 to 125 volts, we're looking at about this point in the graph. So it's going to be looking at, yeah, pretty good. So this FET actually is looking pretty promising, I think. 10 US is much slower than the drive wave that we've got. 1 US up here is pretty much the quickest that this graph goes to. So yeah, that should be pretty good. We've got our ID, which is our drain current. We've got 10, 100, 200, 300 and a little bit. So yeah, that's pretty much good. Let's take a look at what's going on in the live chat. I've been talking for fucking ages. Okay, Headshotter says, look at the MOSFET I told you there. Oh, hello Sam, I've got 60 plus 60 volt PSU with a 50 amp output current. Think you could make a more powerful Class D amplifier out of that? Think I could make a powerful Class D amplifier out of that? Going to be using 75N15 MOSFETs there. 60 volt plus 60 volt PSU. So the way that you'd be able to make an amplifier out of that would be 50 amp output. That's very, very high. So that would, if you ended up making an amplifier out of that, then that would be best at running stupidly low impedance setups. If you've got 2 rails of 60 volts, that's not ideal. I mean, the easiest way to make a Class D amplifier is to have a positive rail voltage of positive 60 volts and then a negative 60 volt rail. You can use just one single positive voltage rail, but it gets complicated. Then you need to have the half rail voltage on the speaker terminals in order for that to work, and then the sine wave swings up from half rail voltage to plus 60 into 0, and that's how it gets the plus minus of the sine wave. So I wouldn't be able to advise you how to do that, because that's way over my head in terms of designing, like converting your power supply into an amplifier. No, too many headaches. It's gonna go to shit. Buy an amplifier. Don't try and convert your power supply into an amplifier. I wouldn't be able to help you with that, unfortunately. One more thing, can the 3000 watts Vibe Deep Space Monobox 1.5? I think that is a 0.5 stable amplifier. Those Vibe amplifiers run the same board as there's a SPL Dynamics version of that, and that is actually a circuit board amplifier design that is designed to run at 0.5 ohms. It's a high current output section, so yes, you should be fine. Unless, with the amplifiers rated 124. Okay, well that's not the one I'm thinking of then. Vibe do make a Black Death or something black, and then I think it's a Reaper. I can't. They make a 0.5 ohm stable amplifier that's about 3K. If it's not 0.5 stable, if it's only 1 ohm stable, then as I said earlier, it's not the amplifier that will predict, that will determine whether it's going to be happy at 0.5. It's your sub setup. So if you have high inductance woofers, an efficient setup, a larger box, etc., then it should be fine at 0.5. That's not something that the amp necessarily is. It's not necessarily down to the amp. It's down to the subs and box and setup that you're using that determines how happy an amp will be at 0.5, not the amp itself. So, okay, I think this is looking quite promising for our output MOSFET. This was literally the first one in the list, so that's kind of cool. Let's go back to Firefox and let's have a look. So that's the thing, though. This is kind of expensive. So we'd have to buy a tube of 50 of these to get it at this price. If we were buying them on their own, this is the Infineon 110N, whatever this is. So to buy that on its own, a pack of 2 is $5.44 each. So that's quite expensive. Is there a cheaper one that is similar specification that will work for 1 ohm loading? I think anything around this kind of mark will be fine. So if we go, oh, here we go. This is quite a jump in price. So 76 amps isn't too far off what we were just looking at. But this is almost halved in price. Let's go for a pack of 2. They're £2.91 each, looking quite nice. IRFB 4127 PBF looks promising. These tend to be pretty decent, these things. So let's go ahead and open this one and open the specification sheet for this bad boy. So our ultimate one that we were looking at just a moment ago then had an extremely low RDS of 10.7 milliohms. So let's go ahead and check this. We have an RDS of, it's a little higher. It's just less than double the on resistance, but it's still a crap ton lower than 60, which is what the original FETs in this amplifier are. So that's still pretty low, not too bad. That's very usable. So we have 76 and 54 amps worth of current drain, depending on the temperature. 300 watts worth of 375 watts worth of dissipation power. Scroll down to the other stuff that we're looking at. Total gate charge, that's quite a bit higher. So this FET will be harder to drive. However, we do have quite a strong drive circuit, so that shouldn't be too much of a problem. But that is less ideal because it is harder to drive. Our input capacitance is 5380. Going back to our other one here, where was that? Going back to our other one here, the input capacitance was similar. Okay, so similar input capacitance there. That shouldn't be a problem at all. These are not too bad looking specs. These FETs should work perfectly fine as well. Let's just check to make sure this FET is happy at the voltage that we're going to be giving it. So we've got drain source voltage versus drain source current. This is the one that we're looking at. So we're going to be going for drain source voltage 1, 10, 100. That doesn't make any sense. This should go up to 200. What? It's a 200 volt FET. Why you not go to 200? Where? 200 volts, yeah. Okay, slightly confused there. This doesn't really tell us the voltage that we want to be looking at. Weird. Okay. Yeah, I don't like the fact that I can't make sense of the graph here. Like, that should go to 200 or higher because it's a 200 volt FET, right? And we're going to be using this at 100 to 125 volts. So I kind of want to see what it's doing current wise at that higher voltage. let's forget that. So we got a couple of ideas for the output FET. So it looks like it's going to be pretty easy. The drive circuit is strong in this amplifier, so we could. I mean, I might just bite the bullet and go for the expensive ones, just because fuck it, why not? It's cool. Or if not those, then maybe something like there we go, 65 amps is a bit less than we're looking at, but the 4227s are actually pretty commonly used in a whole bunch of different amplifiers, including some smaller full range Class D amplifiers, and these are pretty reliable. The power dissipation on these ones is probably not going to be too far off. Again, it's 300 watts, so it might do its power at a lower or higher voltage than the other FETs we've got in there. It's still 300 watts, but it's just lower continuous drain current, which means that it'll probably do its power at a higher voltage than some of the others. So yeah, maybe we'll go for the 4227s because I've seen them used so often, so commonly before, and they're very cheap as well by the looks of it. I mean, I could do with a tube of 50 of these. You can use these to replace the 640Ns and all sorts of bits and pieces in other amplifiers. They're quite easy, they're quite good FETs, and they're driven relatively easily as well. So maybe we'll either go for the 4227s, or we'll just go for the fucking big bad boy ones up here. I'll do a bit more research into that one. Now, with the power supply FETs, let's have a look at those. I'm going to remove all of our filters here for the drain current and the voltage. And we're going to instead filter by a lower voltage here. So we want maximum drain source voltage, and we could get away with using 55 volt FETs to, like, let's go up to the 100 volt because 100 volt has loads in there. So let's go all of these ones here, which will cover our power supply FETs very, very easily. I mean, we might even get away with 40 volt FETs, but it's pushing it a little bit. I mean, 20, yeah, let's do 50 volts. And let's do maximum continuous drain current. It's 110 amps on the 3205s. So let's do from 120 to and up. Wow, what the fuck? 300. I'm curious to see what that 313 amp FET is there. So we've got 305 amps, but there must be something different about that. So let's scroll along and have a look at power dissipation as well. So all these ones are all like sort of 375 watts, etc. So let's go ahead and, just out of interest, let's look at this top one just because it's fun to look at the most crazy one here. So this is, yeah, 305 amp IRL 60B216 N-channel MOSFET. What we got going on here. Curious to see what horrific things this is going to have for having such a high current rating like that. $60 volts. RDS is, wait, what? Fuck! Look at that! 1.5 milliohms? Jesus, that is horrifically low. God damn. Fair play. Yeah, that's pretty goddamn low. That's nice. Okay, cool. So let's take a scroll down and take a look at some of the other specs. Pulse drain current is kind of important because the FETs that we're going to be using, in a scenario that does actually make use of this pulse drain current rating. So if this is higher, then this pulse drain current being higher than the continuous drain current is more important. So 780 amps, that's, I mean, you never end up using that because the FET can't dissipate enough heat to actually make use of that, but yeah, it's there. We've got 375 watts of maximum power dissipation, and let's take a scroll down and have a look at some other specifications down here. We've got where is our, here we go. So our gate charge is pretty goddamn high, 172 and 258. So that's going to be that's going to need some hefty drivers to drive that. You know, I'd say on this board we've only got one NPN and one PNP driving the four different sides of the power supply. Sorry, the two different halves of the power supply there. So we might need to upgrade the drive transistors if we were to try fitting these. The input capacitance, yeah, like I said, with these crazy low RDS FETs, you've got a horrifically high input capacitance of 15570 PF. That is crazy high. That's like, yeah, that's a proper capacitor on the fucking gate, that is. So that's going to be a bitch to try and control with the drive circuit. But the power supply drive circuit is much slower, and so that might be fine. It's one of those things that you don't know until you try it. Modifications will probably have to be made to the gate resistors, maybe the pull down resistors, and other bits and pieces in the drive circuit to keep this thing under control and keep it happy when being driven quickly. So let's take a look at some graphs here. It does its best. Here we go. This is more what I was hoping to see from the graph. It kind of goes up to where it should go. So this will be being used at between 10 and 20 volts. So again, the graph doesn't fucking in the way of the graph here, you stupid ass. I mean, it's kind of hard to tell where the graph goes because the legend is in the way of the bit that I want to fucking read. Why you put the legend there? Like, this is the bit I need. Why not just put it over here? So yeah, this will be driven with a roughly 8 to 10 volts worth of drive, plus minus maximum peak to peak drive waves. So this is going to be like around the top here. So yeah, it doesn't taper off, I don't think, down. So that's fine. When it gets to this higher voltage, that's good. And this is another reason why running your amplifier at a lower voltage, like when you drop to like 9 or 10 volts, when you're busting your amplifier and playing your system, these FETs, a lot of the time will prefer, they'll do better power at a higher voltage anyway. So their current rating goes down as you go down in voltage, and it also goes down as you go up in heat. So that's something to take note of. Drain source voltage, drain source voltage, drain source voltage, drain source voltage. Current. What's the difference between these two graphs? Oh, this is the two temperatures. So yeah, when it's the case is at 175 Celsius, you can see how the graph differs, and it's much lower than it was at 25, but it's not that much lower. So yeah, these look pretty cool as well. So yeah, this is just a general overview on how to kind of look at replacement FETs for this thing. So I'm going to go ahead and order some FETs for this, and in order to upgrade this amplifier to make it stable at 1 ohm, we're going to bypass the internal fuses on the board so that the customer can just use a inline fuse like with most big amplifiers. We upgrade the power supply FETs, upgrade the output FETs, possibly also need to upgrade the rectifiers because the power passes through the rectifiers as well. I will calculate how much current will be needing to be passed through the rectifiers at 1 ohm. If it's getting close to their limits or above, then we'll upgrade the rectifiers as well, which is less of a hassle than upgrading FETs. It's much easier to do that. Like I said earlier, the transformers and inductors are good enough to do power at 1 ohm based on other amplifiers that I've seen. They look pretty decent to me. So the only other thing left to be doing is to be thickening up the traces. The JBL build quality is very good anyway, so we shouldn't really be needing to thicken up the traces too much. They're very nicely built. And another thing we may need to do is we may need to bypass the overcurrent protection on the output section, because if you see on the board here, we actually have these shunt resistors, so these great big bar resistors here, these are incredibly low value resistors that are known to a very specific and accurate resistance, and it's all set up on the amplifiers so that when the voltage drop across these resistors is above a certain point, the amplifier will go into overcurrent protection. So if we're going to be running this at 1 ohm, then we are going to be needing probably to either add some to make this a lower resistance, or just bypass them completely. So we do end up bypassing the the overcurrent protection because we're going to be running this at 1 ohm when it wasn't intended to. So we will probably trigger the overcurrent protection by running it at 1 ohm all day long. So we'll probably have to either make that a lower resistance or bypass it completely, depending on how much time we have and how easy that is to do. But yeah, that's an overview of upgrading this. go with the best of the best. I don't mind splashing out a little extra, says Speaker Freak. Okay, cool. So we'll try the best of the best FETs in this and see if it likes. So what I will do, because it takes a lot more time, it takes a bit more research than what I've done just now in choosing the best FETs. I will go ahead and compare all of these graphs and order the best FETs regardless of cost for this amplifier based on the voltage that they need to do their current at. Not necessarily just the highest current rated ones, because they don't necessarily do the current and the voltage you want. Whew. That's a lot of chatting shit. So the 73N30 sounds like a decent FET. However, we can get higher current FETs than that. We don't need a 300 volt part. So the 73N30 is a 300 volt FET. We can technically get away with running a 150 volt FET on the output section, and we can probably start seeing near to 100 amps worth of current handling on those FETs. 200 volt FET would probably be ideal, which is what we looked at. 88 amps was the highest that we saw. It's out of interest. I'm going to take a look at some of the 150 volt FETs and see if they are like massively different in terms of like massively better. So let's go back to here and let's do maximum drain source voltage 150 and maximum drain current from 50. So let's go from 62 to 104. 13 results. So yeah, whatever the hell these ones are at the top. IRFB 4115 PBF. 380 watts. These are cheap. In a pack of 50, these are very cheap. Considering their performance, they're very cheap. To buy them in a pack of 2 is a lot more expensive. This is the G variant. I don't know what the G variant means, but the fact that it's more expensive possibly hints to it being more desirable. So we have 11 milliohms, which is again similar in, it's the same as the 200 volt 88 amp FET we looked at earlier. Let's open this bad boy up and have a look at the spec sheet just out of interest. Data sheet. So pulse drain current 420, pretty good. I'm going to compare that now to the one we were looking at before. Let's get rid of this. So let's get rid of this, get rid of that. So the pulse drain current of the one we looked at first was 352. So this has the edge on the pulse drain current, which is useful with the output switch. Let's have a look at total gate charge. It is a little higher, 77 and 120, and the input capacitance is acceptable, down at 5 to 70. So this would also work. It looks like it might have an edge over the 200 volt FET, but I don't necessarily think this has got enough of an edge over the 200 volt FET to counter for the slightly reduced reliability by going for a lower voltage FET that's closer to the voltage you're going to be running it at. And another thing as well is to look at the graph, because again, this goes to, this makes more sense. This goes to 150, so we've got 10. No, this doesn't. This doesn't make any fucking sense. Oh no, this is logarithmic. So this is 1. This is 10 to the. I think. No, that doesn't make sense either, because that would be 1,000, and that would be no. What the fuck? What? International rectifier. I don't understand your graphs. 1 volt, 10 volt, 100 volt. Where's my? 150. Okay, so I don't understand international rectifiers graphs. How annoying. Because that could be 10 to the 1, 10 to the 2, 10 to the... No, that could be like 1,000, that could be 100, but then that would be 100, that would be 200, 300, 400. Then it would be giving us a graph all the way up to 500, which is above the breakdown voltage. So that doesn't make sense to me. I don't understand their graph. But the fact that this goes up towards the end is a positive thing, because we would be using this FET right at the top of its voltage rating. So the fact that this FET tends to prefer the higher voltages in giving a higher current, that is a desirable characteristic. So it might actually be better to go with the 150 volt FET in terms of current handling at the voltage that this amp's going to be used at. Yeah. The drive IC is used in a DD-M3B. I haven't actually repaired DD-M3B. Generally, the DD-Ms don't tend to die very often. They're very reliable. But if it's like a 14-legged IC or something like that, if it's a rectangular thin IC with lots of legs, it's probably an IRS 21844S. If it's a more square looking IC that's bigger, it's probably a 2010S. If there's like 3 chips that have 8 legs each, then it will just be a pair of 072Cs and a 211 LM211. What other ones are there? You won't be using an SI, Silicon Instruments chip. The Taramps use those. Yeah, that's probably the only ones it'll be. It'll be an IRS 21844S most of the time. Just opening up my shipment from DigiKey. Parts to fix 4 amps. Crazy logic. Nice. It's always good when you get fresh parts. I got some fresh parts in earlier today as well. It's a good feeling. Means that you can sort it out. They make up to 800 volt FETs. Yeah, they will do. Yeah, there'll be some high voltage applications like 3-phase, tri-phase. What do you call that? Yeah, 3-phase applications where you need a high voltage, and you know there'll be MOSFETs that will be needed to use for step up voltage stuff. Yeah. So yeah, this is what I'll do. So when I actually get the parts in for this, I'll make a live stream where we monitor the voltage and the power before the upgrades, and then we perform the upgrades and see how much cooler the amp runs at its normal 2 ohm load, and then we see how much more power it can do at 1 ohm. So yeah, I'm pretty much going to lock the stream off right about here. The idea of this stream was mainly just to have a chat with you guys really, and see if you had any questions about my trip to the States. I've got another video from the US coming, which will be to do with the new Digital Designs Redline series stuff that they have done big upgrades on. They've completely redesigned the whole Redline series to be much better for what most people want. So that video is coming out in mid-September, probably going to be in about a week's time. I'll drop that video, and that will be really cool for you guys to see. What would be a good replacement for the Kia 7915Pi? There isn't. That's a voltage regulator. It does what it does. There's not really like a better one of that is designed to work in the circuit. All it's doing is it's just regulating a voltage down to negative 15 volts. Yeah, so 7915 is a negative 15 volt regulator. There's no upgrade for that. It's not a MOSFET, it's a voltage regulator, it's an IC, don't change it. Just get the same one. There are different variations. There's like, you know, the 79T15, etc. But generally, they won't have any benefits because they're in these amplifiers. They're not really doing much power. They're just creating a small voltage for the drive circuit to reference, so you don't need to bother upgrading those. LM7915CT, yeah, that would work fine as well. Yeah, generally any variant of the 7915 that you find will work fine. They're not that important in terms of the differences between the models. What do car audio amps have so many chokes? I assume that means why do car audio amps have so many chokes? You don't see this on audio hi-fi gear. What do you mean by chokes? That must be an American term for something. Are you meaning like transformers? What the hell is it? What do you mean by choke? Because I didn't go to electronics school, so I didn't learn any of the terms. I just started trying to fix amps and got okay at it and decided to start making money from it. So what does John mean by chokes? Chokes are coils inductors. I see. So John, the reason that the car amplifiers have so many toroidal transformers and inductors is because car amps are actually a massively stupid thing. Like, in order to create power that drives a speaker from a car, then you need to turn 12 volts DC with high current into a much higher voltage set of rails. Okay, so first of all you need a transformer to change the 12 volts, which gets turned into a switching wave to drive a transformer, into plus and minus whatever higher voltage to drive a speaker, like plus minus 60 volts, plus minus 200 volts, etc. So you need transformers in order to do that, and because these transformers will be passing a fair bit of current and the switching frequency is quite fast, it's actually more reliable to have multiple smaller transformers than it is to have one big fuck off transformer that's doing the whole thing, which is where Taramps I think went wrong, because they use one big fuck off transformer and the power supplies are horrifically unreliable in those amplifiers. So yes, you will tend to find more than one transformer in the amplifier for converting 12 volts into plus minus rail that you need. And then because it's a Class D amplifier, the audio is riding along a fuck off great big switch wave, which is how the Class D amplifier works. So in order to prevent your speaker voice coil from heating up unnecessarily and acting as an inductor, because an inductor is just a coil of copper wire, there is a filter inductor in the amplifier so that the speaker only sees a clean sine wave. You don't see these inductors on a Class AB amplifier because there is no output switching. The transistors in a Class AB amplifier will be emitting a pure sine wave at the transistor itself, whereas on a MOSFET, on a Class D audio amplifier, on the MOSFET you have the audio signal which rides along the switch wave, and you really want to be getting rid of the switch wave before you give that to the speaker. Taramps don't get rid of the switch wave, they let your subwoofer filter it out, which is why if you run your Taramps amplifier connected to your subs idle, then your coils will get very lukewarm. They'll just get a little bit warm. They won't stay stone cold because they are acting as an inductor and they are filtering out the switch frequency all day long. Although Taramps do, because it's a full bridge amplifier, the two switching frequencies are inverted, so there's invert phase cancellation between the switch waves, but it's not perfect, and so the coil does still act as an inductor. Okay, so yes, my friends, stay tuned for multiple live streams going forward from now on. I'm back from the US on a whole bunch of things I have lined up for you guys. I need to finish a Ground Zero 10K, one of the older ones. I've got a DC Audio 5K, which should be good fun. I've got a US Amps, some horrific, shitty 3000 AE thing to try and fix, but I don't have high hopes for that. I've got a Vibe Mono 21K to fix. I've got a Sundown SAZ 1500D to fix, one of the V1s. Got a couple of those to fix, in fact. And just, yeah, general other bits and pieces as they come in. I've got an old Rockford BD 1500 as well. So some nice, interesting repairs for you guys coming up. And also, my Digital Designs Z415 ESPs should be in the UK on Thursday. So there will be some beautiful glam footage and free air excursion videos of those to come as well. So stay tuned. If you are not subscribed, please click the subscribe button. I look at my channel and like my viewers that are subscribed is like 10%. Everyone else, the 90% of my viewers are actually not subscribers. So guys, subscribe to the channel if you want to see new cool content, and click the bell if you want to be notified when I go live, because otherwise you miss that. If you don't get notification when I go live, then by the time you realize I'm live, we will have finished the Amplifier. So click the bell to be notified when I'm live and to be notified for new uploads, and it'll all be fun and games. US AX30, no, it's the 3000. It's not the 3200. It's like it's a rare thing. It's like a something D3000 AE or something. It's yeah, a much rarer one than that. Pain in the fucking ass to fix, I bet. So that will be annoying. So thanks for tuning in, guys, for my return to YouTube live stream. Again, stay subscribed, stay clicked to the bell, and I will see you in the next stream. Bye.